Thank you very much. I'm probably listening to the very end of the last talk. I'm one of those people who is pursuing a particular technology, and so everything I say probably has a little bit of a bias. On the other hand, I think it's very hard to predict the future, and so I think we need multiple options to move forward. And I'll try something here which is a little bit outside of the normal box of how to think about things. So I would like to argue that it is actually possible to get CO2 back out of the air at a price you can afford. And if that's true, it opens all sorts of interesting options. You can make fuels out of it, or you could bury it, depending on what you want to do with it. So let me just sort of, as a matter of disclosure, say I started to think about this in 1999, in 2003, in the winter of 2003 to 2004. Wally Broker introduced me to Gary Comer, who used to own Land's End. And Gary got very interested in climate change issues, and he got interested enough that he put money up to form a small private company with which I have been involved since. So I have an interest in this which goes past the academic side, but I would argue I'm interested in it because I started it. And so I leave it to you to decide to which extent I'm worrying about the academic issues and to what extent I'm worrying about more commercial issues. But I do think it is one of those fundamental things which can change how you think about the problem. So without arguing to begin with, can we do it? Let's assume we could do it, and why would it be interesting? And I would argue the biggest first step it gives you, it separates the sources of CO2 from the sinks of CO2, because the air is a conveyor which can transport the CO2 over large distances without really a big side effect. You could imagine having a car driving in Los Angeles, and it emits CO2 into the atmosphere, and that CO2 will mix in very well, and in a matter of weeks it sort of has circled the globe. In a matter of months it has spread out in a hemisphere. In 2 years it has spread out between the two hemispheres, and since we are not worried about the change in a matter of months or weeks in the CO2 in the world, we could literally pick up that CO2 in the Australian desert and dispose of it right there. So you are not tied to your source anymore. You suddenly have the ability to make things happen far apart. The other thing you could start thinking about it is the emissions could also be emissions from the past. So you can start reducing the CO2 content of the atmosphere again if you really can do that. But of course this makes no sense until you stabilize CO2. Before that, you are just another sequestration option, another capture option. Ultimately, I think what makes it really interesting is the idea that it allows for closed fuel cycles where you have CO2, the ash, coming from the air. You take it with new energy and convert it back into a fuel. And then, of course, from a practical point of view, in the short term, there are commercial applications for CO2, which allows us to sort of have a bootstrap from where we are to where we would like to be. But the underlying problem, of course, is the problem of CO2 in the atmosphere. And this graph is only to highlight some of the issues with that. And the point I want to make is this graph here, which is labeled continued exponential growth, is simply saying we keep doing more or less what we were doing the last 100, 200 years, and this would go off the chart before the century is out. The point I really want to stress is if in 2010 we had figured out how to stop the growth in emissions and hold emissions constant, we would follow this curve. So if you take the European view that 450 parts per million is sort of the limit you should get to, in my view it really doesn't matter that much anymore whether you held things constant or whether you kept exponentially growing. You just delay the time you breach that boundary a little later. In other words, in many ways the problem is like a stock problem rather than a flow problem. Roughly speaking, half of the CO2 we put out, and you see this sublinear behavior which comes from the fact that some of the CO2 ends up in the ocean. This is a simple impulse response model which allowed for doing this. But what you really see that over hundreds of years, roughly half of the CO2 we put out actually stays in the atmosphere. And then it's simple arithmetic. 1 gigaton of carbon is worth half a ppm. If I say half of it gets away, I need 4 gigatons of carbon to add 1 ppm to the atmosphere. We are currently putting out 8 gigatons. a year, and so you can now figure out how much time do we have before we hit the 450 mark, and we can quibble on the 10% realm whether I got the factor 4 right, or and that also depends on whether you are fast or slow, because there are some time constants absorbing some of the CO2. But my point is, we really have to come down to drastic reductions, and it's not good enough to just go after the power plants, because the power plants are only a third of the total, roughly. So you have to go after the distributed sources as well. So to give you a feeling, if 450 ppm is the number you deal with, you can then say, well, this is 60 ppm lift. We have breached the 390 recently, so we are 60 ppm away. Times 4 is 240 gigatons of carbon. Divide that by the average population in the next 50 years of 8 billion people, and you have 30 tons per person. So your per personal allowance is a truck like this. This is about 30 tons of gasoline, and so think of having that parked in front of your house, and every time you go somewhere, every time you fly somewhere, a little of it is taken out. In the scale at which things go in the US, that tanker truck is empty for the average person in roughly 5-6 years. So that sets the scale of how tough it is to actually hold the 450 mark.
Excuse me, is this for all life?
This is for not just your life, this is for the life of your children and children's children, because this is a stock problem. So I basically said you have a total budget of roughly 30 tons per person left, and I took a slightly higher. Yeah, and that's this could take infinitely. You could do this infinitely long, but if you truly, you have a few hundred years. If you make the time constants much longer than that, you see other processes picking up the CO2.
Yes, but population is decreasing.
I used 8 billion people to get 30. So I allowed for that roughly. But we can quibble whether it's 40 tons or 25 tons. Right? But the point is the budget is surprisingly small. And there's nothing new in this number, but people don't tell it to you this way. And if it's told to you this way, and I'm in an airport, and I see all that jet fuel being put into my airplane, I start feeling guilty. So it is quite possible, and some people will tell you that the 450 ppm mark is clearly too high. I see no practical way to actually stop at 450. We probably will overshoot that. But we may have to come down even lower than that, and some people have suggested 350. And I would argue without having air capture as one of your tools, you really can't even do that. So it seems to me we have to think about whether this is possible. And just as an end of the introduction, let me point out the problem is not self-limiting. There is enough fossil carbon in the ground that we probably could have 5,000 gigatons of carbon. So we could go to 2,000 ppm if we chose to do so. It's not that we are limited. Coal resources are estimated somewhere between 3,000 and 5,000 gigatons. These are not proven reserves. There's a difference there. And people argue about what precisely are the proven reserves. And I think part of it is what precisely do you mean by proven reserves? And so it's what you could do at current price. But assume there is no more oil and there is no more coal, but there are still 4,000 gigatons of coal in Alaska. We do figure out how to spread that over the rest of the world. But right now, nobody in his right mind would count it in the reserves. Right? So what's growing very rapidly, particularly in the US, but also in China, is shale gas. So we really are at a point where you might actually even see gas to liquid substituting for coal. I would actually argue a price well above $100 a barrel is not economically sustainable, because if people were sure that you couldn't come down from that anymore, I think alternatives like gas to liquid or coal to liquid would actually enter. We know it can be done more cheaply than that. And in a way, all those resources are fungible, making all those fuels on the other end. And so I would conclude that without carbon capture and storage, fossil fuels have to be phased out. And as a corollary, I would say liquid fuels in the transportation sector also would have to be phased out, and their capture cannot happen on board. An airplane cannot carry home the CO2 it makes, even if you could figure out how to capture it, and because it can't handle the weight, because it's 3 times the weight of the fuel. And your car, you would have some 6 big cylinders of CO2 in the back of your trunk by the time you get back to a filling station to refill the car. I don't think it's practical to even consider the option to do this on board. So, as I probably have said here in a talk before, I really see only 3 big options which are big enough to give 10 billion people energy at the scale we in the developed countries take for granted. So you need to think in tens of terawatts, and I think the 3 options which are big enough are solar energy, nuclear energy, and fossil energy for maybe 100 or 200 years if you fix the carbon capture and storage problem. And so I think it's very important to really seriously start thinking about how to get all 3 to the scale you need. And if you get rid of the fossil fuels, then the other 2 have to figure out in some way or another how to deal with the transportation sector. And in my view, the best option there is to provide liquid fuels. So, and I would argue air capture has a role in all of these cases, because if the answer is fossil fuels, then carbon capture and storage is needed. And I would argue CO2 capture from the air is capture of last resort. If you have something which is cheaper than that, by all means go ahead, but cars and airplanes and then are unavoidably going into the air. And I would argue they're fugitive emissions. If you're talking about a power plant, roughly 10% of that will escape, and it's getting economically expensive to get it there. If geoengineering is the answer, and I don't talk about that here, then you can think of the reduction of atmospheric CO2 and stabilizing it at the desired level as a geoengineering option. And again, I think you would need the capture of CO2 just to keep it cold and let the CO2 pile up under it. Doesn't make sense in my view. It's a little bit like saying we solve the garbage problem by putting houses on stilts and we raise them every year a little, because that's what you would have to do, because the CO2 levels would keep going up and up and up. And I think if you have non-fossil infrastructures, you need energy storage and you need transportation fuels. And again, air capture would allow you to do that, because it would bring you in the carbon atoms you would want to close that loop. So, and I would make a pitch for liquid fuels on boards of vehicles rather than electricity in form of batteries. And the simple argument I'll put forward, this lithium-ion battery, if it's a high performance and is roughly 0.5 megajoule per kilogram, this tank of gasoline is roughly 50 megajoules a kilogram. There's a good 2 orders of magnitude difference between the 2. And so not even knowing anything about it, if you had battery cars working well, and I came along and say, replace that battery with a fuel cell, you suddenly would have your 200-mile range changed into a 10,000-mile range, and so you could fill up your car once every year. So clearly people would like that transition. There is some intrinsic advantage to those liquids, and I think it's worth trying to fight for them and see whether you can have them. So, having told you why I'm interested, now let me give you a brief summary why I A, think it's possible, and B, how we go about it to make it possible. So, the first observation I started with was nearly coincidental, because in some entirely different context, I started to ask myself how much CO2 is actually in a cubic meter of air, which has roughly 40 moles of air, and 1 part in 2,500, 400 ppm, would give you roughly 1.6% of a mole of CO2 in that cubic meter of air. And if you now say I need an energy equivalent because I want to think in energy terms, I say, well, if I combust gasoline and make that much CO2, how much heat do I actually release? And it's a simple arithmetic, it's 10,000 joules. What struck me is that we build windmills, and the windmills go after the kinetic energy of that same cubic meter of air, and it's a simple calculation. m/2 v² is the kinetic energy, and if I go into a place where you would put a windmill at about 6 meters a second, you can calculate mv²/2 to be 20 joules. So what struck me that day is there was a factor of 500 in favor of the CO2 concentration in the air over the kinetic energy. And so I left this with the feeling this is worth looking at a little harder, because if there is so much more CO2 than kinetic energy in the air, yet we think we can build windmills, one should investigate this a little more closely. And so basically, if you build some CO2 scrubber, this is just sort of an artist concept how it might look. The thing which is interesting is it's orders of magnitude smaller for the same carbon reduction than a windmill. So after looking at some costs, I said, well, if I'm really dumb about it, this is right when I started, I'm going to say this has a capital cost, and it has a certain per square meter of frontal area. That, let's say, has the same. Let me calculate the price of a ton of CO2. If the price of electricity is 5 cents a kilowatt hour, and then I need one more assumption. I say the collection efficiencies of those two are maybe the same, 30-some% or whatever you pick. And if you make that assumption, you find that the price of 5 cents per kilowatt hour is equivalent to 50 cents per ton of CO2. So I said I could be orders of magnitude off with this calculation, and maybe it's 10 times more expensive. But what it suggests is that contacting the air passively, just to extract the CO2, is not where your cost is likely to be. And we actually found that out in the future as we now, going back from 1999 when I started to think about it to today. If you actually add up all the cost of the material we have to hold in the wind, it's not that high. It may not be 50 cents, but it's not much more than $5 a ton. Right? And I think we can actually drive it even below that if we keep working on it. My point is the contacting is not the issue. But on the other hand, once you have contacted the air, and the CO2 had to be absorbed, because I cannot afford compressing the air, I cannot afford heating the air, I cannot afford cooling the air. So all I really can do is have a sorbent in there which binds the CO2, and now my job is to get it back off whatever bound it, because I can't imagine that I can get some stuff I can throw away with the CO2, because it would usually be too expensive. So I need to have a regenerable sorbent, and now I look just like a power plant flue gas scrubber, except I need a stronger sorbent, right? And so I can take their costs as a lower limit of what I could possibly do. I now have absorbed the CO2 on some material X. It could be calcium hydroxide, it could be sodium hydroxide. I'll show you something better in a second. But whatever it is, I now have to rip the CO2 back off and repeat this. And this sounds just like the job they have. And so the question is our job much, much harder than theirs, or is it comparable? And I would argue, yes, the concentration is roughly 300 times lower, but that's not as bad as it sounds. And the reason I'm making that argument is that if you calculate the sorbent strength you need to absorb down to a particular level, I start at 400 parts per million in the atmosphere, so I have a very tiny amount. And I'm not after creating CO2-free air, so I'm perfectly happy to stop at 300 or 200 ppm and say that's the end of the line, because I want CO2. I don't want CO2-free air. Whereas the power plant has to take nearly all of it out, and so therefore they have to come down to 1% or 0.1%. So the factor is not 300 anymore, but it's around 30. And then thermodynamics is with you, in that the sorbent strength only scales logarithmically in that number, right? And so as a result, for every factor 2, I'm less concentrated. I need an extra epsilon in energy. And it turns out here I plot the actual curves, and I cheat a little by pointing out that the power plant has to be a little hotter. They probably are at 350 Kelvin. I may be at 300 Kelvin. I may even be a little lower. But taking those two numbers, you see this is the range for the power plant. This is 99% capture. This is 10% capture. And this is where air capture would be in the sorbent strength. So my point is, I'm not particularly much stronger. I'm a little stronger, but not particularly much stronger. So as an aside, people say, well, he did the thermodynamics wrong, and therefore don't trust his answers. So I actually sat down and worked it out carefully, and the answer is the free energy of mixing is not that simple RT log P. It's this RT times this whole long thing. So I worked it out, and I said, well, if I just take an epsilon out of the air, and I just take the tiniest little bit, and I take that limit of this complicated formula, I go through this, and I get my RT log P. So my point is, the people who said he's wrong actually calculated a number which is slightly lower than mine. So if I just take the free energy of mixing, I could be out here and take nearly all of it out, and I would sit on that black line. Whereas I would have said, I need a sorbent which can do that, And that's an irreversible process because the sorbent has to be stronger and got you all the way from here down to there. Right? And so for most CO2 molecules coming in, it was too strong. So I needed a little more energy. And by the way, as I go to 0, it would go to infinity. So we are roughly 8% more than the fancy formula would suggest. But that's because we assume we do it in a single sorbent. And so we then find out that we have a certain efficiency we can get to. So, but the conclusion I have from that is that the dominant costs are likely to be quite similar. Right? And in the end, the proof is in the pudding, I would argue. I can't go much more with back-of-the-envelope statements as saying that I see it as reasonable that the final cost of collecting CO2 from the air will be higher than scrubbing a flue gas stack, but it will not be orders of magnitude higher. I need a sorbent which is 20–30%, maybe 1.5 times as strong, and so the energy I need to close the loop is a little higher than theirs if we are in the perfect limit. So if they argue they can get down to $30 right now, and some people say, well, we could do it at $15 a ton, well, we have to see where they end up, and if they get gradually perfect, we would be maybe 1.5 times their cost. So I would argue we can get quite cheap as well, and that's sort of what drove us to make it happen. But then, of course, what becomes very clear is your sorbent choice is central. Right? If you have a good sorbent, you can make this work. So we looked at all sorts of things, and we started like everybody else. You can take sodium hydroxide, and sure enough, it works. It works very well on the capture side. It's very cheap on the capture side, but now the CO2 is really bound, and you can't get it off easily. And so we finally ended up with a resin material, an anionic exchange resin, which is a polystyrene, and it has very interesting features. It's quite cheap. It's made by the truckload, quite literally. You can buy it from Chinese vendors right now at $2.50 a kilogram, and it loads up. And when it's dry, it absorbs, and when it's wet, it gives it back. So here's your polystyrene with a quaternary ammonium attached, and that acts like the sodium in a sodium hydroxide solution. So now the negative ion, when I buy this stuff, is a chloride. I washed it out and made it a hydroxide. Not surprisingly, it will pick up a CO2 and turn into a carbonate. What surprised us, it picked up a second CO2 and it turned into a bicarbonate. And in moving from carbonate to bicarbonate, a sheet of this material, and let me see here. Here you see that we actually had it in sheet form. A sheet of this material is still as fast as a 1 molar sodium hydroxide solution covering a similar sheet. So the upshot is the kinetics is as good as sodium hydroxide, but I'm moving from carbonate to bicarbonate. That alone got us excited because the energetics of swinging between carbonate and bicarbonate is much more favorable than the energetics of swinging between hydroxide and carbonate. But then we found out that if the dry resin will do that, the wet resin actually falls back to the carbonate. And that we call the moisture swing, and we got really excited about this. So here you see some of this material in various forms. And so the sheets absorb CO2 from air. They absorb down to very low partial pressures. If they're empty, you can easily go to 1 or 2 ppm in the air. Air loading can reach bicarbonate, and the equilibrium is water sensitive. So we had experiments set up, like a bell like that, where we did it inside. Then we replaced it with a small loop where we go around. And so you see here data where the red line is the CO2 content in the gas space. So if it goes up, the resin releases. If it goes down, the resin absorbs. And the blue line is the moisture in this. So we had ways of changing the moisture level in the gas. And so you see whenever we make it dry, it absorbs CO2. Whenever we make it wet, it gives it back. And so we can swing it back and forth as many times as we like. Here's an isotherm. So this is the loading of the resin as function of partial pressure when the air has about a dew point around freezing. So this is desert air in Tucson, Arizona, as a matter of fact, where we'll be doing things. And so you see this nice curve as it loads up, and notice at 200 to 400 ppm. It's essentially fully loaded. Here is the same curve at slightly different temperatures when the material is wet. And notice the change is essentially in the scale. These are kilopascals or percent of CO2, whereas the previous scale was ppms. So basically, the scale shifted by roughly a factor 100 to 200 and stretched out simply by making things wet. Now, what we believe happens is that in the wet system, we see the same carbonate chemistry as you see in aqueous sodium carbonate solutions and bicarbonate solutions, whereas when it's dry, the individual ions will hang on to a hydroxide and convert it to a bicarbonate, but the neighbor doesn't know about it, it's too far away, and so the bicarbonates are there all along, all the way until it's full. You also see that the maximum loading falls off if I make the air too moist, so it won't work very well in the tropics. It works very well in a desert, but we believe we can change the resin. For the engineers in the room, we actually changed the thermodynamic argument once more a little, because what we have is dry air coming in, and then later liquid water, and what comes out is CO2-enriched air and moist air. So we pay a part of the energy bill by the simple fact that there is free energy available if water evaporates. So in a funny way, half of the energy penalty to get from CO2 in the air to have liquid CO2 is paid by evaporating water. Right? And so we cannot stop using water, because if we did, we had no energy source. But if I poured this water here on the carpet, which I probably shouldn't do, but in a couple of hours it would have gone away, because there is free energy to be had spontaneously, it will move out. So if you look at the steps, we have dry resin absorbs CO2 from the air. That lowers its free energy. Then the resin is wetted, which really shouldn't do anything. Maybe if anything, the water arranges itself to lower the free energy even more. And then it releases spontaneously CO2. So clearly this is again downhill. And then the last step, which you have to account for as well, and I think that's why people were concerned about thermodynamics, the last step is the resin dries. And that happens spontaneously in the air, in the wind. So we don't add that as work. So we work a little bit like an air conditioning system in a desert climate, which makes things cool by evaporating water. We have the water release the CO2 again, and then in the end, for the cycle to close, the water actually has to evaporate. And so we roughly consume cubic meter, 10 kilograms of water per kilogram of CO2. But if I translate this into a cost, it's tiny, even if I had to desalinate the water. By the way, I could afford that. And I can think of it as a source of free energy, which costs me roughly ½ cent a kilowatt hour. So from that point of view, using water, I think, is completely justified in this case. So basically, we have these things in the air. We put them in a box and make it wet. Now we have two options. Either we evacuate the box before we make it wet, then we get 5% of an atmosphere of pressure inside, which is CO2 and some water vapor, or we put it back into the air, then we have 5% CO2 in the gas stream. And at this point, we didn't pay much energy at all except for the water. And now you could go with a conventional process and close the loop all the way to the top. I think it's smarter. Well, we can debate that, but I believe it's smarter to actually evacuate. The alternative is to capture it a second time. And the question may be what kind of energy you have. If you have electricity, then it's nice to run compressors and pumps, which you have to do if you have a vacuum-based system. If you run a second sorbent, you may use heat to close the loop. So here's sort of a small picture of something which could do it. We assume we have 1 meter a second going through. Our uptake rates are around 25 micromoles per square meter per second, and so are our release rates. So we have a specific surface area. This is older. We are better now of 4 square meters per kilogram. This is not the tiny nooks and crannies in there, but it's the layers of the material itself. And so we fill the filter volume with about 10% of the stuff, and the upshot is if you wanted a ton a day, you would look at a system which is about as big as a container. It would sit on top, and you could move the whole thing around in such a container. We have then worked out what that might cost. And the point I stress is people always tell you, well, it's the cost goes linearly in the concentration. We would argue we're in a regime where it still goes linearly with a log of the concentration or the dilution factor. Right? And I think that's an important argument. And people give you a counter who say, well, you know, if you look at ores you mine, then indeed it goes, the cost of the metal is linear in the dilution factor. And this is known as Sherwood's law, and you see this beautiful plot here. But notice it's log-log, and I want to point out how much lower bromine from seawater is, and it's because it's not a rock. If you calculate where the slope comes from for all the mining, it turns out there's a similar slope for pharmaceuticals, which I think has similar arguments attached. But if you calculate it for mining, what you get is that the price of a metal is roughly $10 per ton of ore. And if you ask, what did you just pay for? You paid for digging up the rock, for crushing the rock, for grinding the rock, and do the first extraction. Anything beyond that is in the noise compared to those first terms. So in that case, it's clearly the linear term which dominates, because the big cost is the mining and getting rid of the tailings. Whereas in our case, we are passing air through a system. That's not where the cost is. The cost is still in the second step, which here tends to be invisible. So I think this argument is simply not right. So we did first cost estimates. I could spend an hour on this here, and I don't want to do that unless you're really interested. But basically, we found the materials cost in our devices is low. The manufacture cost the first time around is very high. And we figured that 1 ton a day unit the first time is $200,000. Right? The operating costs, the inputs are very low. The maintenance is high, because if you're a ton a day and you have 30 minutes of a person there, you just spent $30 a ton of CO2. Right? And so we figured the operating cost is about $120 a ton on the first try, and we end up with a total cost somewhere between $200 and $250 per ton of CO2. That has built in a return on the investment. I would like to stress this is a first of a kind. So if I came to you today and said, you know, you need to build a car in a machine shop, you also would have a $200,000 item on your hands. And as a matter of fact, if you build a car out of spare parts, it costs more than that, because spare parts are priced much higher than the car itself. So I do believe that there is an enormous amount where learning can drive costs down, and factors 5 or so are actually not that horrible. But I do want to translate these costs, and I do want to point out that $100 per ton of CO2 would translate into 22 cents per liter of gasoline, or if you're in this country, 85 cents per gallon. If you get it down to $30, this is 70 cents per liter of gasoline, or 25 cents a gallon. The other number I want to point out, that gasoline, a liter of gasoline has roughly 10 kilowatt hours of chemical energy in it, because I'm going to use that number in a minute. So this sums up why I see this as interesting, because even at $100 a ton, it starts getting interesting. I think at $30 a ton, this would be cheaper than any carbon tax I could imagine, because you end up actually doing have your cake and eat it too, as they say. I'm not as concerned. There was an APS study which said the costs are going to be horrible, and their particular process was estimated at $600 a ton. I have to say I agree with it. When I estimated the same process, I came up at $1,000 a ton. So within some small factors, we tend to agree. But I think if you take that point of view, you couldn't build an electric car, because I calculated that the Tesla avoids a ton of CO2. If it really avoids it, it doesn't emit it from the tailpipe. It may emit it at a power plant. But the cost of moving it there costs you roughly $600 a ton of CO2, taking their cost for batteries into account. If you look at fuel cells, if you look at batteries, if you look at photovoltaics, all of these, or wind for that matter 30 years ago, all of these start out at prices which are an order of magnitude higher than you in the end need. And I think there's a fundamental fallacy in estimating costs up front. And I give you the example of one of those little CD-ROMs. The first one I bought, I spent $20 on. Right? Today, they are about 10 cents per disk. Now, my point is, in 1980, if I asked you to make a reasonable cost estimate, you couldn't have come up with a proper cost estimate telling me 10 cents a kilowatt hour, because if you had, you would know how to do it. And so there's a paradox there, right? You can't predict where prices will end up. And I think the honest answer is we will not know. But just because you are a factor 5 too expensive at the start doesn't mean you couldn't get there. That's my point. And so you have to be careful. If you just make an incremental change, I think it's fine to calculate the cost and say, I do or do not want to make that incremental change. If you start talking about new approaches, new technologies, I think you have to say, are there some physical laws which say you can't possibly do it? And if that's the answer, well, then you should forget it. But if you just say manufacturing costs are high, you can't really make an argument. And I think the thermodynamics, I can calculate how much heat I would need to make this happen on the order of 60 kilojoules per mole. And I can ask how much does it cost to provide that? It's cheap, right? If I ask how much does the material cost? It's cheap, right? I can't do it with low cost right now to pull it all together. But that is precisely where learning can make a difference. So then you can say, well, maybe it's worthless because you couldn't possibly get to scale. So let's assume I stay with the 1 ton a day unit and I mass manufacture them and I bring them out to where you would want them. I'll give you an example. You may think of having a small oil well which benefits from enhanced oil recovery, but it's too small to justify a long pipeline. So we could put 10, 100,000 units in that place in order to provide the CO2 to run this EOR. But whichever we end up doing, if you had 10 million units out there in the market, I think you're starting to be a real player. You make a difference. And the argument is if you have 10 million units at 1 ton a day, give it 360 days in a year, you have 3.6 gigatons of CO2 per year. That's 12% of the world's emission right now. So at that point, you are a player. Assume they last 10 years, then you have to build 1 million per year in order to maintain your stock. And you should compare that with building 70 million cars and light trucks. And again, I would argue, if they are $200,000 built in a machine shop, their cost and complexity is not that much different from what you would expect from building a car or a small truck. So the order of magnitude you have available in current production capacity out there actually far exceeds what you would need. Then if you wanted 100 million units out there, everything has to be scaled up by a factor 10. But you could still do this. And by the way, you know from this, because there are a billion cars parked somewhere, there's actually room to put them. And people have a tendency to put them in a row and then say, oh my gosh, you can cross the United States several times to collect enough CO2. I would like to point out, because I did the calculation, if you take all the windmills in the US right now and put them side by side, they will cross the continent and then some. So it seems to me, if air capture is interesting and feasible, first place it could play a role is creating a net carbon economy with fossil fuels. So in such a world, you would have to dispose of the CO2, and I don't want to talk about how to do this here today, but you would also need it from the concentrated sources, and it would be silly to let it out and then run after it again from the air. But you have roughly half of all emissions which come from distributed sources, and that would be a niche for air capture. In order to make all of that work, I think ultimately you would need a rule which says for every ton of carbon coming out of the ground, another ton has to be put away. So if I had to do cap and trade, I would do it directly at the well and say, you dug up carbon either as oil or as gas or as coal. You are mobilizing so much carbon. Show me a certificate of sequestration that you put an equal amount back away. Now, in the short term, you would have permits and credits to balance the books because overnight nobody can put that much carbon away. But you would have a promise that this gradually goes away. And so you would be left with doing it this way. And of course, air capture could play a role in this market. It's not the only one. It could be the utility, which gives the coal plant, the coal mine, the CO2 sequestration certificates, which come from that coal directly. But of course, they will fall 10% short. And I think the long-term promise has to be that it's a one-to-one. Right? If that were the case, then you can think of as air capture as being part of that mix as one of the capture options. And I think it's the capture option of last resort, because it can deal with any CO2. It doesn't care where it came from. And of course, lower capture options come first, right? So if your power plant can do it at half price, by all means, take the CO2 at the power plant, right? But more expensive options simply cannot compete anymore. So as a result, air capture becomes the marginal cost. It will set the marginal cost if it is playing at all. And it has advantages too. Right? Air capture eliminates transport costs. If you are here in New York City, no matter how well you captured your CO2, you won't have much of a chance to get it out of here, at least at exorbitant prices. So you may, in certain places, prefer to emit it because you can't afford the transport. It opens remote sites. If you think of mineral sequestration in Oman, you have enormous deposits of serpentine there. There's no practical way to move them from there, and it's not practical to move CO2 there except by wind, and then you have air capture. And you can deal with past emissions, so you could actually say that government agencies start tearing up certificates of sequestrations in order to get excess, and then you could actually come down that curve. Lastly, I think there's an ultimate application for this, and that's making synthetic fuels. And I believe that the two complementary energy carriers in the world are electricity, which is very responsive to demand, no emissions at the point of consumption, stationary applications it's just ideal for, but it's very difficult to store. Right? And on the other side, you have liquid fuels. They are very easily stored. I think that's their claim to fame. You can have a tank out in a harbor, a big container, and the cost of that per kilowatt hour of stored energy is incredibly low. So you can actually have the gasoline in there for a year or two, and the extra cost of the gasoline is actually quite small. You can store it for the transportation sector, but you could also store it for the electricity sector. And I would argue if you have seasonal storage or even weekly storage, batteries are way too expensive to make this work. And it has an extremely high energy density, but it does put out CO2 at the point of use. And what connects the two carriers, I think, is electrolysis and fuel synthesis. So you have low temperature, you can make hydrogen from water with solid oxide fuel cells. At high temperatures, you can make CO and hydrogen from CO2 and water. And then once you have synthesis gas, or CO2 and hydrogen for that matter, you can have hydrogen, you can have methanol, you can have dimethyl ether. And if you have those, or you start again with synthesis gas, you can make gasoline and diesel. Exxon has a process to go from DME to gasoline. Fischer-Tropsch can go from CO and hydrogen to gasoline and diesel. So there are ways of closing that loop. And the ingredients in a liter of gasoline, to just put this together, would be at $50 a ton of CO2, roughly 10 cents of carbon dioxide. And at 50% efficiency, recall the 10 kilowatt hours I gave you a minute ago, you would need 20 kilowatt hours of electricity to make a liter of gasoline. So if you're off peak, that could be as little as 40 cents. So my point is, taking all of that together, I actually have the ingredients to think about how to make this happen. So in the past, people talked about the hydrogen cycle, and they sort of had this view, you have a power generator which separates water into oxygen and hydrogen. The oxygen is released, the hydrogen goes to your consumer, and the consumer produces the power when he or she needs it, and the water gets back into the environment. Now first, because I talked to EDF, I made a little change to my diagram, but to just point out, load leveling also applies to nuclear energy, except the other way around. Wind is on or is not on. You guys like to run on a level keel, right? So you could have it equally well like that. But then my point is, if I have air capture working and you give me CO2, I can make you any hydrocarbon you like. And that's the argument I made a second ago. And that car runs a lot more easily on a liquid fuel, which may be methanol. It doesn't have to be gasoline anymore. But what's nice about storing energy in carbon compounds is that it's a very simple storage, and it's a very compact because it has very high energy density. So that way you can close the cycle. So I see carbon neutral energy systems, they could happen with all sorts of things. I lump together nuclear and renewable energy here because I feel those two have in common that they don't produce CO2. You have coal, tars, and shale, that's sort of the dirty fossil. You have natural gas, which is getting bigger and bigger right now, and you have petroleum. And the petroleum sort of naturally feeds the liquid fuels, and everybody else somehow or another ends up in electricity. And through synthesis gas, everybody could end up making liquid fuels as well. So you can now look This is sort of the closest we could get to fast. We could have petroleum for a long time, so this feeds into the liquid fuels. The mobile energy demand is satisfied, air capture collects the CO2, and the CO2 is put away in carbon capture and storage. The renewable or nuclear sector just goes along and may satisfy stationary energy demand, which I think ultimately will beat coal plants which have to store their CO2. I think you have a real chance there to get cheaper. But the alternative, of course, is that if the world were to run essentially on natural gas, we would make synthesis gas and electricity. The synthesis gas would feed into the liquid fuel, and everybody would do carbon scrubbing, which goes into carbon capture and storage. But the last option is everything comes from here. No more CO2 emissions at this end. But now you would like to have synthesis gas to have liquid fuels. They satisfy the mobile energy demand. Air capture gets you your CO2 and water back, right, which is then put back into the synthesis gas with energy which came from the electrolysis and electricity from over here. So I can have it both ways. And by the way, this can now act as feeding the transportation sector, but it can also feed the storage sector for the energy side. Because one of the things which hit me, which is a very simple calculation, if you take a lithium oxide battery, and I'm now purposefully pessimistic because numbers get easy, $1,000 a kilowatt hour stored. Some people say it's down to 500. So if we take 1,000 to have a simple rule of thumb, 1 penny an hour is roughly 10% on a $1,000 investment. So if I have because there are nearly 10,000 hours in a year, right? So if I have a $1,000 investment and my clock ticks at a penny an hour, maybe it clicks at 2 cents an hour because you want a little higher return on this, right? If anything, I'm low, right? And so that takes care of your $500 on the other side. But if it's 1 penny an hour and I have a diurnal swing on my battery, I'm in for 25 cents or 24 cents a day, a kilowatt hour right here. And I haven't paid for the fact yet that my battery may only have 400 cycles, in which case I'm clearly dead because I added more than $1 on that. But it is that what gets me. It is not the price of the electricity which came in. I could have lost 2/3 of it if I had off-peak electricity from a windmill at 2 cents a kilowatt hour. This only would drive me up to 6 cents. So the fact that a round trip through chemistry is never very efficient may actually not matter if the cost of the electricity when I put it in was cheap. So I'm actually not afraid of that, and I would argue if you can get cheap electricity, you can solve your storage problem on the chemical side and forget all the other options. They are just a bonus if you get them. So to me, and this is where I wanted to close this talk, this is sort of a grander vision where to go and why I think air capture has such a central position in all of this. Because notice, it doesn't really matter which of these big energy infrastructures will be the ones who win in the end. They all can benefit from having the ability of having air capture, and on top of it, you have the argument we may find ourselves in a situation where there is too much CO2 in the air already. So some people accost me on this, to put it mildly. They say, this is really evil what you are doing because it just gives people an excuse not to do anything, right? And I'm pointing out, you don't really want to get into this fight with one of your hands tied behind your back, right? And you may find out that even with best effort, we have to come backwards in the CO2 in the air. And I can't think of anything else but this which could do it. And to put it in perspective, the uptake rate of this 1 ton a day unit, if it were a tree of a comparable size, which I can well envision, it would collect tens of tons over its lifetime. Right? So this is supposed to collect a ton a day. So we are roughly talking about a factor 1,000 in collection efficiency between biomass and this approach. As a consequence, by the way, all the algae folks who want to make algae-based fuels found out that they outstripped the ability of the algae to collect CO2. They like to have some ways of collecting the CO2. But that's sort of a side issue where this could go. I'm just trying to point out that the energy systems in the future could benefit from having liquid hydrocarbons around, and if they do that, then they need air capture, because for every ton of CO2 going in the air, it has to come back out. And if you think biofuels, they have to do it too, because they just happen to do it by natural photosynthesis, but it is air captures of sorts. So if there are any questions, I'm happy to answer. I think I've got through my slides, I believe. Yes?
Yeah, maybe I can follow everything in terms of techniques, because you are speaking about a device in which you are able to capture this Anionic system. So, but do we have any experiment right now according to the performance of such device, and which allow us to figure out that the figures you put out are good in terms of future? Because okay, on the paper it seems very nice, but according to the techniques, is it relevant right now? When it will be relevant? And what kind of product do you produce, and how we can recycle?
Yes.
I don't understand everything.
Well, I would expect it takes a little longer than me hurriedly going through a lot of slides. But I would argue we are building small prototypes at this point. We are not yet at the ton-a-day device. We have worked over the last year quite diligently inside the company on getting much better than the 25 micromoles per square meter per second, and to make the specific area much better. So this is where things are now. I think the next step would be to scale it up to 200 kilograms a day or so you can actually do precisely what you would like to do. The argument, I would say, at this point, a lot of this is still in the paper stage, right? But practically speaking, I now have materials which actually do absorb CO2. I can get the CO2 off. Those experiments are done. Where I'm still falling down, I would argue, the underlying molecular mechanism is semi-understood. I can hand wave my way through and say this is how it works, but if we try to pinpoint it precisely, I would like to do a lot more experiments to make that work. But I have a characterization which says this is the partial pressure of CO2 if I make it wet, this is the partial pressure if it's dry. In a dry climate, it takes so long for it to dry as it is exposed to wind. So there's a lot of those details there, but I think the next step is actually to move out and to do just that. And I would agree with you. And I think at the end, you only know after you did it whether we turn out to be $200 a ton and never get off that number, or whether we can actually systematically drive the cost down. And here I'm the optimist, because otherwise I wouldn't be working on it, who says I think those steps can be done, but I think that there is a chicken and an egg. Right? You actually have to put the resources in and make it happen, and then see whether you can go from there to the next step. From the company's point of view, they would love to sell, so that gives you stepping stones. Let's say we start at 5% CO2 in the exit stream. So no evacuation, you just make it wet, you collect the CO2 at roughly 5%, and you feed it to algae, right? Because they want to buy CO2. Or you feed it into a greenhouse. In the Netherlands, which is not the climate we would like to work in right now, they pay roughly 100 euros for a ton of CO2 to feed it into a greenhouse, right? Where they dilute it back down because they want to be 900,000 ppm inside. So we would nicely be a fit to a greenhouse which wants to keep the doors closed and thereby contain heat and thereby also operate at elevated CO2, which tends to grow tomatoes faster. So it is a productivity enhancement for them, and that's why they pay $100 euros a ton of CO2 to make this happen. Right? There is an 8 million ton a year market in what I would call merchant CO2 in the US. Once you get into EOR, there are 40 million tons. So, but none of that is big enough to really deal with these big issues. But I do believe, because it can start small, that you can actually sort of bootstrap your way up. Whereas if you are at a power plant, you have to start big, because otherwise you didn't prove anything. So my own, but this is a whole other talk, my own view is these units don't want to get particularly big. They want to get mass produced. Right? And then if you want 1,000 tons a day in a place, then you have to aggregate 1,000 of these units into one place. But implicit in this is a fairly sophisticated level of automation, because if I spend 30 minutes of maintenance every day on a unit, I just blew my budget on labor cost. right? So small units aggregated requires a high level of automation and sophistication that way. But I do believe ultimately the proof has to come from doing. And that's why I'm still engaged with private enterprise on this, because otherwise in a university setting we can talk about this for another 20 years. And it will gradually get more and more sophisticated in our understanding, but it won't get much more practical. Yes?
Yeah, the question I had was a similar one. If I understand correctly, the size of that unit currently looked like the size of a 20-ton container. Is that right?
Yes, but it doesn't have 20 tons of stuff in it.
Yeah, but it's the size of a 20.
Yeah, it's a 40-foot
so then,
shipping container.
So
Yeah.
then, just looking at it, the numbers you showed, I think you wanted 100 million of those.
Yes, and there are about 50 million such containers out there.
So where would we, and then that comes to the point that you parked for today, which is the environmental impact of placing 100 million of these 20-ton size containers,
Mm-hmm.
and what the planning associated with that, and where would you put them? So I understand the capture, I understood the synthesis, but the actual storage, where do we actually put
Well,
them?
assume for the sake of argument right now, Australia has made the claim that they have enormous saline aquifers inland somewhere in the Australian desert. Right? They have aquifers there because that's what they want to inject in. One of the complaints people have about injecting CO2, you raise the pressure. We could use some of the water, which I didn't show you. If you do the calculation for desalinating seawater, and so you would look at brines which are not extremely saline. If you look at that, that would add roughly $5 to a ton of CO2. So we could afford that kind of level of energy. So if you are now in that desert, yes, you would create a big cluster of them and put 10,000, 100,000 in one place, and they would inject CO2 underground into those reservoirs. The point is you would go where you know what to do with the CO2, not to a random place. Right? So you would be on top of a storage facility. Or you would be, if you're in enhanced oil recovery, you would put them up into the field where you want the enhanced oil recovery to happen, because one of the advantages you have, the transport was free for you. So you would like to go where you can use the stuff. So as a result, I'm also keenly interested in eliminating the humidity limit we have right now. Right? The material sort of rolls over from a state where it absorbs into a state where it desorbs, and unfortunately it starts doing that at a humidity you might have in Singapore. Right? And so I would love to modify the material so that that transition happens at a little higher level of humidity, right? Because I'd like to be capable to work in any climate, right? And therefore go to any location, right? But I feel from a starting point of view, if I can get a foothold in a desert and show this works, I have started. So then I can afterwards worry how to get it into a different climate. But there are competitors out now, they say we use a thermal swing. Right? So they have to say how to pay for all the heat. We have to say how do we pay for all the water. Right? And since they are thermal swing, they are pretty insensitive to the water.
We have time for one additional question.
You choose.
We get to.
Hi.
Sorry, when this is a little bit of a challenge, I guess, but when I booked my flight to come to New York, there was a box that popped up on the website
Yes.
that said, do you want to offset this journey? When I bought my car, actually, recently, there was another thing you could do with the manufacturer that said, do you want to offset the lifetime emissions of your car? And that seems to be all be related to planting trees somewhere.
Yes.
You know, and that kind of feels to me like, you know, without getting too much involved in the politics and the emotion around that, but it sounds like quite a good way of doing it, because it doesn't consume, you know, other resources to achieve that.
Assume I have $30 a ton, right? The lifetime emissions of a car are on the order of 100 tons of CO2, right? So for an extra $3,000 at $30 a ton, you can make a single car lifetime carbon free. Not the time you hold the car, but lifetime carbon free, because they last on the order of 10, 12 years, and you may have sold it after 3 or 4. So yes, you could do that. You could have a tanker coming into a harbor, and you can say the 300,000 tons of oil on board, which are roughly 1 million tons of CO2, has been neutralized up front. So these are, to me, bootstrapping ways of getting into this. I think ultimately you need a government regulation which says you have to buy that offset. Right? This is a voluntary offset, and I think right now people are not willing to pay $30 a ton, and certainly not the $200 a ton where we think we'll get our foot in the door. But it turns out in Phoenix, Arizona in 2008, because I paid attention that year, a ton of CO2 in that local market was selling at $300. And the reason this is the case, because the CO2 is basically driven by the transport cost, and it came from Los Angeles, where it's $50, and the ride on the truck for 500 miles or so, ended up driving the price up to $300 a ton. So there are niches where even with the higher prices you can start. But ultimately, yes, this is the offset, and I just suggested ultimately you have to mandate that. In the short term, you can get volunteers. And sort of the order of magnitude is thousands of dollars per car. Yes?
Once you capture the CO2, you talk about storage and you talk about recycle for fuel for vehicles. Are there other solutions available or in research?
There are smaller scale options, but it turns out the amount of CO2 we make is just very large, right? In the US it's 20 tons. I don't know what it is in France. I would guess it's probably 7 or 8 tons of CO2 per person per year, right? So if you look at those kind of numbers and say, what do you do on that scale? Well, this 20 tons in the US would be 50 tons of carbonate a year, because you have to go energetically downhill if you don't turn it back into a fuel, and the only thing downhill are the carbonates, right? So you end up saying, okay, how many Greek revival columns can I put in front of my house, because I can make 3 or 4 a year, right? And so you pretty soon, we don't consume things short of water on that scale, right? And so I see plenty of smaller things. You can get into the concrete market. You can get, people talk about cements which are carbonate based, and all of those things can absorb a little here and a little there, but in the end you took 1 ton a day, 1 ton a person a year away, and you are left with a 19 at the other end. So I'm looking at the big options are disposal, right? And people call it storage, which sounds so much more benign, but really it's disposal, or recycle to what it was, and that is fuel, right? And that means you had a cheap energy source in your back pocket, because otherwise you can't afford it. Yes?
Did you make a global energy balance of that last slide? I mean, because the Fischer-Tropsch transformation is quite energy intensive. For 1
yes.
kilowatt of stationary demand, 1 liter of fuel, how many kilowatt of nuclear?
We looked at various options, and this is early. I think 50% efficiency is ambitious, but not outrageous. So if you were to look at these various options, electrolysis can be a lot more than that, and you can push Fischer-Tropsch into the 50-60%. So if you multiply this together, you can aim for about 50%, right? So basically you need, and that's what I included when I said 40. I assumed it costs you 20 kilowatt hours to make a gallon of gasoline, rather than the 10, which is what's chemically in it, right? And round-trip efficiencies, you can get to 1/3, right? So by the time, if you started with electricity when it was cheap and you ended up with electricity when it's expensive, you probably got 1/3 back.
Unfortunately, we have to close that. So please Join me in thanking Professor Lackner